In 2010, inspectors at a heavily secured industrial facility noticed something that made no engineering sense. Centrifuges were failing at nearly triple the normal rate, physically damaged beyond repair, while every control room display showed completely normal operation, every reading perfectly nominal. The facility was air-gapped, deliberately disconnected from the internet specifically to prevent exactly this kind of remote interference. The cause turned out to be software anyway. It came to be known as Stuxnet, and it's widely considered the first cyberweapon in history to cause deliberate, targeted physical destruction. Essentially, all malware up to this point was built to steal something: data, credentials, money. Stuxnet was built to break something physical with extraordinary precision while actively lying to the humans monitoring the process about what was happening. It specifically targeted the industrial control systems, the programmable logic controllers, or PLCs, that govern the physical speed of uranium enrichment centrifuges, and it was engineered to alter that speed just enough to cause mechanical failure over time, while simultaneously feeding fabricated normal looking readings back to the operation watching the control panel. The facility's air-gapped system design was meant to make remote attack essentially impossible. Stuxnet's creators solved that problem by not attempting a remote attack at all. The worm was designed to spread via infected USB drives carried in physically by contractors or personnel with legitimate facility access, whether or not they had any awareness of what they were carrying. Once inside, it was engineered to spread specifically toward the exact industrial control software it was built to target, while remaining dormant and undetectable on any system that didn't match its intended target profile. The technical sophistication involved was, at the time, unprecedented. Stuxnet exploited 4 separate, previously unknown Windows vulnerabilities, what security researchers call 0 days, to move through connected engineering networks undetected, an extraordinary expenditure of rare technical resources for a single operation. Since each 0 day represents significant independent research investment, once it located its specific target, Siemens industrial controllers of a particular model configured in a particular way, it altered centrifuge rotation speeds through cycles specifically designed to induce mechanical fatigue and failure over time, while simultaneously replaying pre-recorded normal sensor data back to the facility's monitoring systems. So operators watching the control room saw nothing unusual at all. Stuxnet was not discovered through security monitoring at the target facility. It was discovered almost by accident, after a coding flow allowed it to spread beyond the intended target and infect unrelated computer systems around the world, eventually triggering a technical support call from an unrelated company experiencing unexplained crashes. A Belarusian cybersecurity firm, Virus Block, ADA, identified the anomalous code in mid-2010, and it took the broader security research community months of painstaking reverse engineering to fully understand what they would actually found. Malware, unlike anything previously cataloged, purpose-built to cause deliberate physical destruction rather than theft or disruption. The story of how Stuxnet actually escaped its intended target remains only partially resolved, even more than a decade later. For years, the most widely accepted explanation was simple human error: a worker unknowingly carrying an infected USB device between the air-gapped facility and an internet-connected computer. A 2019 investigation by Dutch journalists, later partially collaborated by officials from multiple countries, suggested a more deliberate chain of events. Intelligence services had allegedly recruited an engineer with legitimate facility access to physically introduce the malware rather than relying on chance. Whichever account is more complete, the underlying lesson holds either way. A facility's air gap is only secure as every single person and device ever granted physical access to cross it. And the human perimeter proved to be the actual point of failure, not the digital one. Stuxnet's significance extends well beyond the specific facility it targeted. Security researchers and military strategists have since treated it as the definitive proof of concept for an entirely new category of weapon, one that can achieve strategic physical objectives once reserved for airstrikes or sabotage teams without a single person crossing a border or a single missile being fired. Subsequent incidents, including attacks on Ukraine's power grid in 2015 and 2016 that caused real documented blackouts, drew direct methodological inspiration from techniques Stuxnet pioneered, establishing what security researchers now describe as a fundamental era in industrial control system attacks running roughly from 2010 through 2016 that essentially created the modern discipline of operational technology security as its own specialized field. The most durable lesson from Stuxnet, and the one that echoes directly through the grid security and critical infrastructure resilience work we have discussed elsewhere in this series, is the physical isolation alone was never a complete security strategy. It was always one layer, dependent on every other layer, including the humans who cross it, holding as well. Modern operational technology security now assumes exactly this, that a sufficiently motivated, well-resourced actor can eventually breach a perimeter, digital or physical, and designs for resilience and detection after that breach rather than betting everything on the perimeter itself never failing. Stuxnet is, in the truest sense, an origin story. The moment the abstract idea of a cyber weapon became a demonstrated physical reality with consequence that could be measured in destroyed machinery rather than stolen data. More than a decade later, its central lesson has only become more relevant, not less, in a world where software increasingly controls physical infrastructure. The line between a digital vulnerability and a physical one has effectively disappeared. Thank you so much for your presence. I hope you have enjoyed this as much as I did. And I'm looking forward to your comments. If you have any questions, reflections, feedback, feel free to leave them in the comments. Make sure I will proactively answer them as soon as I see them. And I'm looking forward to welcome you in another lecture. Till then.